All right. All right, since you guys went through RNS already, you should be able to figure this out. So these are directly from your textbook, actually. I know a lot of you said to go over practice problems, so that's exactly what I'm going to do. So what is our first priority? Looking at this one here, what's our first priority? BR. Yep. Second. So obviously, third, fourth. Remember that little trick? I'm assuming that Chris taught you guys, but cover up what's in the back, cover up what's dashed. So just act like that's not there. 1, 2, 4. Right now we have R, but what we covered was a 1 or a 3. And so we flip. You guys got that down already in SI, right? All right, so last section, somebody got confused on this one. So for example, this center here, what's the first priority? Dylan's saying F. Does anybody else concur or no? Anything else? Yeah, it is F. Some people got confused and said this is BR because BR is inherently bigger, but you're looking at the direct attachments from this carbon. So the first one is going to be 1. And so because these both are carbons, we're not looking at not only the carbons, but we're looking at what makes them different, and what makes them different is what those carbons are bonded to. So this carbon is bonded to just a couple hydrogens, and this carbon is bonded to a bromine. So this bromine one is going to have the higher priority. 2, this carbon, 3, an implied hydrogen, 4. Cover up what's in the back. It doesn't matter what priority it is, what atom it is. Cover up what's in the back. So we act like that's not there. 2, 3, 4. So it happens to be like the other example. Right now we have R, but what we covered was a 1 or 3. So we flip to an S. And a lot of people, they like try to overthink the clockwise and counterclockwise. Don't even worry about that. I don't really give a hell. Give a shit, whatever word you want to use about the clockwise and counterclockwise. We've all driven before. If you're turning the steering wheel to the right, it's R. R, right. And the left is S. So don't even worry about clockwise or counterclockwise. If you're turning the thing to the right, it's R. Hopefully that made sense. So somebody said that they didn't get to Fischer projections yet. And that's exactly what this is. So a Fischer projection is just like this, but in 2D. And so we're going to go from this 2D to 3D. And so to look, we often look at it like a cat or a dog. We're going to call what is here, what's on this row, an arm. We're going to call it on an arm. And what's on these, a head and a tail. So the heads and tails are dashed. And what's on an arm is wedged. Again, we're just going from a 2D Fischer to a 3D. And I'm just going to put X. So X. So for Fischer to assign RNS, I personally I don't like to keep everything together. I like to split it in half. So right now I'm just splitting this in half. That's what this is. So here's the top portion. And here's the bottom portion. So what would be the first priority? Yeah, CL. What's the second? So again, this is X, Abigail, that's correct. Because again, we're looking at this right here. Again, I'm just splitting this in half. So here is a carbon that's attached to hydrogens, just hydrogens. Here we have a carbon that's attached to all this other bigger stuff. So we have 2, 3, 4. Christy, does that make sense? All right. So for Fischer, unlike the 1 and 3 trick, you don't really have to, this is the kind of like the other trick you have to know. You don't really have to worry about covering anything. So you just go from 1, 2 to 3, 1, 2, 3. Right now we have R. But the thing you have to remember is if your lowest priority is on an arm, again, these are what I'm calling arms. These things are what I'm calling arms. If your lowest priority, in this case, this hydrogen, is on an arm, then you flip what you got. Everybody get that? So this carbon here, this chiral center, really is an S because when we got R, we realized that our lowest priority is on an arm. And so we flip. Does that make sense? I don't know if you guys are writing anything, but if anybody needs me to say that a little bit slower, let me know. I'll write it here as well. You don't have to worry about covering. If the lowest priority is on an arm on your Fischer, then you flip what you got. Isn't the lowest priority on an arm? So somebody asked a similar question before. Sometimes your lowest priority isn't exactly where you usually expect it. So your lowest priority might not even be an H. It might be a BR or a CL or an OH. It might be anything. So your lowest priority might not always be on an arm. So for example, if I were to just change things up hypothetically here, I could have my hydrogen like that. Cl, and have my methyl here. So Christy, I'm answering your question here. So hypothetically, you don't always have to have your lowest priority on an arm. So all I did was just change the locations of the atoms and where they're bonded. Here, the lowest priority is on the head or tail. So you wouldn't have to flip what you get with this because your lowest priority isn't on one of the arms. Does that answer your question? Right. And so, have you guys heard of enantiomers or diastereomers yet? All right, so a lot of people try to go through the mental gymnastics and try to make model kits and try to rotate all the bonds and everything. Just RNS it. A lot of people make this chapter the downfall of their grades of this exam. This chapter is what you make it. If you know the tricks, then you're solid. And so, for enantiomers and diastereomers, if if hypothetically these carbons were S, both of them were S, you're often going to see things notated in parentheses, and you're comparing it to this one, and these are both the complete opposite, then they're enantiomers. Okay? If all of the chiral centers are opposite RNS, then it's an enantiomer. They are enantiomers to each other. But if not all but some, so if this is SS, this is RS or SR, so not all but some of the chiral centers are opposite, then it's diastereomer. So let me write that for you guys. All chiral centers are opposite RNS. Then they're enantiomers. Diastereo, not all but some are opposite. Does that make sense to everybody? So don't try to overcomplicate it. If you get something like a Fischer, or you get something like this, just do the RNS of your chiral centers and remember this. And for Fischer, here's your trick. All right, does everybody get that? What about meso compounds? Luckily, I have an example for you. So, again, like last week, I try to make things simple, and sometimes some people have that 1 and 3 trick, and for the back carbon they have 2 and 4. But I personally prefer, I don't know about you guys, but for organic chemistry, I want to have to memorize as least as possible and just apply my concepts. So I just say fuck it to the 2 and 4 rule and only just do the 1 and 3. And so you just go from Newmann to bond line. And so remember from last week I was teaching you this. So this methyl is up on the plane. We're looking down that bond. Our back carbon, the methyl is pointing down. So what's on the right side is wedged. What's on the left side is dashed. So what's on the right side of the front carbon is our hydrogen. And what's on the left side is our chlorine, otherwise what I call dashed. Similarly, like the back carbon, what's on the right side is wedged. So we have our chlorine. On the left side is dashed. We have our hydrogen. So now you can just do your regular 1 and 3 rule. You don't have to remember both rules. For 1 and 3 is your front carbon, and 2 and 4 is your back carbon. If you feel free, if you want to memorize that, Chris is going to show you. But I personally don't. I don't like it. I prefer to only remember one thing rather than 3. And so I just go from Newmann to bond line and do my regular RNS. But what can make something meso is if you have an internal plane of symmetry. So that's what you have to be careful on. And this is directly from your, if you didn't notice, this is directly from your textbook. When I took this course, this example came up word for word on my exam. And so he's probably not going to get more complicated than this. And so for meso, you have to check if you have an internal plane of symmetry. And how we do that is we can rotate along this bond. So if we rotate like this, you rotate, that front carbon turns on itself around this bond, and if you rotate the front carbon, keep the back carbon the same, you get this here. And so, therefore, you see that there is an internal plane of symmetry. And if you were to do the RNS, you'd see that these are opposite to each other. One of them's R, one of them's S, one of them's S, one of them's R. And so if you have that internal plane of symmetry across each other and they're both opposite RNS, then it's meso. So just to give you the answer right now, this Newmann here is the meso compound. And so just to help visualize the rotation with the Newmann, remember, again, this bond can rotate. If you were to rotate, again, not 60, not 90, but if you were to rotate all the way around, your new, just the front carbon, your new Newmann would look just like this. And if you were to make this 2D, you get that. And therefore, you see the symmetry in this, right? And so you have the internal plane of symmetry. Your front carbon has one RNS, your back carbon has the opposite. And if that's the case, then you have a meso. Does that make sense to everybody? I have another example here. Again, if you have this example, you can rotate about this bond. We're just rotating this chiral carbon, and we get this. We have this internal plane. I don't know what is what, but let's just say this is R. This is S. It could be S, R. But if they're opposite and you have that internal plane like that, then it's meso. Just like this one. I actually did this one. This one is R, this one is S, but we have that internal plane of symmetry. So even though there is chiral centers in this, so what makes something chiral is it has it's 4 different substituents. It can rotate polarized light, and if something is chiral, then it can act as an enantiomer. That's something that that's a definite conceptual thing you're gonna see. Things that are chiral can act as enantiomers. But if there's that internal plane of symmetry and it's meso, then it's overall achiral. And therefore, it also can't act as an enantiomer. Does everybody see how I'm walking through this? How to get these meso compounds? All right, well, that's about as complicated as it could get, really. So let me use, I have the end of chapter buttons here. Let me see if there's something I'm going to show you. Oh yeah, also, if you have something, if you have if you have an example, it's in your textbook. I don't have it with me right now. I don't have the ability to show you it because I have these printed out. But cis and trans, it's very often, I noticed it. I don't know if you guys hopefully will notice it, but if you guys look closely enough across the double bond, because the double bonds can't rotate, so with double bonds, if you have a molecule that has a double bond, it can therefore be cis or trans, right? And if it's cis or trans, if one is cis and other version is trans, then they are diastereomers. So let me just draw an example of it. So we have this double bond here. We have our wedge bromine. And a methyl. And to compare, we have same thing, but that double bond changed. You just put MET, met, for methyl. So again, this double bond shifted positions so that it changed. This is trans, this is cis. As you can see, this chiral carbon stayed the same. But if that double bond changed from cis to trans or trans to cis, then they are, in comparing to each other, diastereomers. Does that make sense to everybody? I'm teaching. Any questions about that? Does that make sense? All right, so let me just add that note to the other. All right, so again, guys, don't overcomplicate it. If you're comparing two molecules like here, do the RNS for the chiral centers. If one has your RNS and your other molecule, the chiral centers are all the opposite, then you have enantiomers. If some of them are, but not all of them are, then you have diastereomers. If you have a double bond, it's very likely, I mean, I'm sure there's an example out there, and maybe Chris will go over it, maybe Jermaine, but it's very often that if you have a double bond when comparing to the other, if one is cis and one is trans, then they're diastereomers. And again, with the meso, you have to look at the internal plane of symmetry. If you rotate about the bond like this, and you get a mirror image, and the RNS for the chiral centers are the opposite, then you have a meso compound. And therefore, it's overall achiral. So you could try to throw something at you. I mean, it's not really a trick question if you know your shit. But he could be like, again, which one is meso? Maybe none of them are. That's why you have to check. That's why you have to rotate and check. But for this example, this one is your meso, because if we were to rotate about the bond, if we were to rotate the front carbon all the way around, we were to see that the front and back carbon are exactly mirror images, except the front and back carbon are opposite RNS, and therefore that version is a meso. So that is basically all I have for you today, guys. That is really as complicated as you can get. Again, this chapter can be the downfall and what hurts your grade for the exam, this coming exam. But if you remember these tips and tricks, not only with the 1 and 3, but this one here for Fischer, because I can almost guarantee you're going to see a few Fischers. If you remember these things that we're teaching you to get through it, and you are able to apply it to almost all of your questions, and therefore it is as easy or as hard as you want to make this chapter. So, yep, I'm going to stay back for a few minutes if anybody has any particular questions, but I'm going to go ahead and finish up because that is all I have for you today, guys.